Welcome to this quick tutorial on how to use the new 3D Truss solver, 3D space frame solver on Degree Tutors. So here we are on the Degree Tutors Labs site. This is the main courses page. If you want to get to the solvers, you just go to StructureWorks, and these are the only two solvers that I have up here at the minute. There's plans for quite a few more different solvers, different structural analysis solvers and design tools here. So there is the 2D solver, Truss toolbox, which I said has been live for a while. Let's just jump in here very quickly. So this is the solver toolbox that I talked through previously, and if you want to see a tutorial on this guy, just hit this tutorial button, and there's a video here. It looks a little bit different because I've updated the styling a little bit since then. So let's jump over to StructureWorks again. Right, so that was a 2D. The 3D solver, this is the new one, and this looks, you'll see, exactly the same, pretty much the exact same. And of course it is the exact same because it's just a 3D version of the 2D thing that we already built. And so we've got one extra dimension to deal with. Now, I've worked in a few extra things that, well, I consider them improvements. Some of them are very useful. Some of them are less useful. You'll see them as we move through this. But just to sort of orientate you quickly here, right? You've got the 3D viewport here. We've got a whole panel of options over here. We've got a few buttons down here, which I will get to. And then you've got your main data entry area. So the things you have to define when you're modeling essentially a 3D truss, right? You want to know where your nodes are. Okay, you've got to define your nodes. You've got to define your elements, and also we'll put some material properties in here as well. We've got to say how our model is restrained, and then we've got to apply some loads to our model. Now, one thing that a lot of people asked me for after I released the 2D solver was to include self-weight, because in the course that this structure is based on, which is this course here. So this this solver is based on this particular course. It's basically just a web implementation of what we build in this course. But anyway, in that course, we take into account the self-weight of the structure. And on the 2D Truss toolbox, I didn't have that option. So now I have included it here. So when we've filled in all of our information, we can either click to include the self-weight within the calculations or not include it. And so it's not included by default. And then hit solve, and then a whole lot of other stuff will appear here once we have some results. All right, so let's just work through sort of pushing some example data through this, right? So just as with the 2D toolbox, we've got an example data button here. If you click that, that will open up this page here, which is just a Google sheet, which is, you know, freely accessible. Anyone can get to this and have a look. This is the structure. That structure is a kind of a lattice tower. So that structure is defined by the data that you see here in the green boxes, and it's only the data in the green boxes that we're going to copy and paste and bring over to our solver, right? And you know, you look at this and you say to yourself, well, like, geez, how are you going to generate all of that? The only way, practically speaking, to generate these models is using a modeling tool. If you follow any of my courses, you know I'm a big fan of Blender, and that's what I do all of the modeling in. And that's why with this particular solver, I've included a Blender template modeling file, which we're going to talk about in the second half of this video. So yeah, well, we'll get to it. So let's jump over here and let's just get this into our toolbox, right? So I'm going to select in the green box here all of the nodes. So what am I doing? Command Shift right arrow and then down arrow to select all that. Copy, and let's jump over here and just drop it straight in. Okay, so we can see we have some nodes in here. We'll focus on them now in a second. Let's just bring in the members next. So what have we got? With the member number, just sequentially numbered. We've got node I, node J, Young's modulus, the cross-sectional area, the yield stress for the member, and the member self-weight. All right, let's just select all of that, bring it in and drop it in there. Okay, that's fine. Next up is the restraints. Okay, so what this is saying is node number 1 is restrained in the X, Y, and Z direction, and the same for the other 3 nodes here. And we could change those restraints if we wanted to release. Obviously, this is a truss, and so these are only translational restraints. There's no rotational restraints here. So if we wanted to change any of those, we would just type in false. That's basically that. So let's take that and drop it in over here. Okay, that's fine. Jump back over and force data. This is, if I recall, this is applying a 5 kilonewtons in the negative Y direction. So that would mean looking at the thing down here, that would mean pointing downwards, essentially. Let's just take that and drop it in here. Okay, there we have it. At this point, we can just either include or not include self-weight, whichever we like, and then hit solve. But before I hit solve, I'll just zoom in a little bit here and just have a little look at our 3D structure. The first thing I want to do here actually is I want a bit more vertical real estate. So I'm going to come over to my view options here and expand this, and I'm going to increase my window height, right? So I'm just going to move that slider along just so I can basically make use of all that extra space I have. I'm going to turn off my applied forces, and you'll notice when I change something, the view snaps back to a default view. That can be helpful, but it also can be a little bit annoying. So you can turn it off, so we can tick that box and turn off reset viewport on update. So now if I change my view and I make some change here, like show those forces again, you'll see, or node numbers in that case, show applied forces, you can see the view doesn't snap back. That's how you do that. You just uncheck reset viewport on update. So let's have a little zoom in here. The first thing you'll notice is we can change cameras, right? So what you're currently looking at is the structure in orthographic. That can be pretty handy, an orthographic projection. But if you want a more realistic view, which is true to what we would see in the real world, you can change that to a perspective projection. And now it's a more, I guess, realistic is loosely correct term. Let's just have a little look around our model here. So the elements themselves are, we can control the look and feel of those. Now that's not important, right? If you're just here to do some structural analysis, it doesn't matter what these look like. But because I'm a bit of a 3D modeling geek, I like to play around with the look and feel of this, and so I've left in these options just in case you want to play around with them, right? So you can increase your ambient lighting or decrease it. You'll notice that we've got some shiny elements, and if you look closely, you can see there's an environment map. Doesn't matter what that is if you don't know what it is, being reflected in the members. It just means they have a kind of a realistic look. Now the reason I'm telling you this is because if you've got a big model, you might want to for performance reasons do away with all of that extra fancy rendering and just have a more simple looking element. So expand materials here and just turn off better materials, and you're just left with a kind of an ugly looking but easy and for your computer to render simple material. But I'm going to leave that like that because it just looks cool. All right, so let me just sort of zoom back out here. One other thing that you'll want to know is this thing here, scale slider. That just increases the scale of your elements, just to make them easier to see, basically, depending on the scale of your structure. We could show wireframe or not show wireframe, show node numbers or not, and you've seen show applied forces or not. Okay. So that's kind of all of the viewport options. Let's just sort of leave those where they are. So let's go and solve. Let's go and solve this particular structure. So I won't bother with self-weight for now, and I'll just hit solve. So we've submitted the job, we've got it back. Okay, and you got your results back when you see a nice axial force color bar down at the bottom here. So you've got a color scale essentially, which will correspond to the colors of these elements when I go and view the axial forces. And if you're wondering what all the little green vertical lines are, those green vertical lines, that just indicates that you have one member with this particular axial force. Is it useful? I don't know if it's that useful, but it kind of gives you an idea of the distribution of the distribution of axial forces within the members in your structure. You can see how they're distributed across the scale. Obviously the ends of the scale are set by the maximum tension and compression forces. Okay, so scrolling on down, we've got our analysis report is the first thing we see here. So the analysis report is just gives you a quick overview of whether or not things went well or not, whether your analysis was successful. Green ticks across the board means yes, everything went fine. We can proceed and look at the results. If you see a big red X somewhere in here, it means something did not go fine. And even if you get results back, you're going to want to ignore them. But green ticks across the board means everything went okay. And so these tables of data are the same as for the 2D solver, with the obvious addition of an extra dimension. So we have our reactions table, we have our axial forces, we've got axial force magnitude. Of course, you can reorder the tables based on ascending or descending. We've got stress utilization here. And then we've got our displacements, X, Y, and Z, and then displacement magnitude. So if you're going to be doing, we're just having a quick look at the solver here, but if you're going to be actually doing some analysis, you're probably going to want to download the data and pour over it in your own sort of probably Excel file or something, but so you can do that no problem. So let's have another quick look up here. So what have we got? We can view our reactions, and we can sort of zoom in and investigate those in the 3D viewport. That's just helpful just to get a quick visual cue as to whether or not they make sense or not. So we'll just turn those off. Axial force, so we can, if we switch on to view the axial force, the sky disappears, and we've got a dark background just because it makes it easier to see the colors. And so the colors of all of our members, if you've used any structural analysis software, you know what this is telling you. It's just giving you a visual representation of the force magnitude in all of your elements. You can turn on, so that's a continuous scale, that's where the color is indicating the load magnitude. We could go for a binary scale where we just have tension and compression indicated. That can be helpful as well. We can show the force values again. That's not very helpful. So you're really going to want to zoom in to a particular area of interest and perhaps then turn on your values, and you'll be able to see the force magnitude in each of the members. Okay, so let me see, what else do I need to show you? The next thing is probably deflections. Let's turn that off and turn on our deflections. Okay, so let me see, deflection scale. So, well, you can scale it up and scale it down. Basically, it's just a deflected shape. There's nothing really too dramatic to say about that. Probably be a bit more interesting if we changed the loading on the structure. Maybe I'll do that in a second. And of course, for any of the nodes are the nice shiny red things. For any of the nodes, we can sort of investigate what is the X, Y, and Z deflection. You got to go down to the deflected node, and you can determine what the X, Y, and Z deflection of any of your nodes is. All right, so that's, in a nutshell, that is the 3D Truss solver toolbox, just an extension of the 2D toolbox. But it's handy. In particular, I have in mind, students doing projects. You just want a quick frame solver, and you want a nice way of generating some interesting models, and then getting a force distribution for those models, some deflections. I see a lot of students jumping into ANSYS and doing finite element modeling, which is the wrong kind of modeling to do for this kind of structure anyway. This is a nice handy tool for you to use, and so that's what it's there for. So go ahead and feel free to use it. Right, so that marks the end of the first part of this. That's how you use this toolbox. Second part is basically, how do you go ahead and generate a model, and more importantly, the data that defines that model. How do you do that? And so for that, we've got this modeling template. So that's what I'm going to talk about next. Let's get on and do some modeling, because really this tool only really is it's only really any use if you can generate some models that you can then feed into it. And so let's just see how you do that. So I've included, if you hit this button, I've included a modeling template. So that should download a template file. There it is. Okay, so this is a blank Blender file that has some scripts included in it that will basically look at the model you've just built and generate some CSV files that capture the data relating to that model. So let's just open it up here. We are over in the Blender file. Now, before I open this, I just took it from my downloads folder and put it onto my desktop. I'm only telling you that because when I run the scripts that export data from this file, it will drop those CSV files into the same location as the Blender file. So just keep that in mind. All right, so it's a standard Blender file. It's a slightly modified arrangement of windows, but that's not really important. What we can see here in the center is the structure that we've already analyzed. And so what I'll do, just to kick things off here, is I'll just generate the data or export the data for this structure just to demonstrate how you do it. So over on the right hand side here, we've got a text editor, and this is where the scripts live. Again, if you're new to Blender, completely new to Blender, I'd say, or direct you over to the course that I referenced in the earlier part of this video, where I give you an introduction to Blender and how to do some modeling, structural modeling in Blender. I can't really get over all of that now, it's too much to cover, and so I'll just give a quick overview here. Really, the idea is to give you enough of an idea so that you can see the utility in generating your models in Blender and using the solver to solve them. There's 3 scripts here, right? So there's a script here. You don't, unless you want to, you don't have to edit anything down here. One thing I will say is don't change the name of the file because it's hard coded in here. So you'll see modeling template 3D truss. That name up there of the file matches that name. If you change the file name, change it in the scripts as well. Okay, so I'd suggest just don't change the file name. So what you got to do in this one is above the dashed line here, we can set a Young's modulus, a cross-sectional area, yield stress, and self weight. That will apply those properties to every element within the structure. If you want different properties for different elements, you've got to go ahead and either generate, what's the best way of doing it? The best way is to dive into the CSV file and edit manually in there. It's very doable, not too hard to do, but I'm not going to focus on doing it in this particular tutorial. I'll just apply those default properties, right? So there's nothing to it. All you really have to do is just hit that play button there. That runs the script. And if I jump over to my desktop now, you'll see that there's a couple of CSV files. Is there? There is. So we've got nodes.csv, and you'll notice that that is the exact same as that there. Okay, that's because that's where I got the data from to put it over into this Google Sheet. And we've also got elements.csv. So all you would do at this point is open that guy up, select all of that, copy it, and jump over here and come in here, and you just paste it in there. I won't paste it in because we've already done it. So that's how you generate the data. So that was the nodes and the elements. Next, you'd want to, what would you see? Well, you'd want the restraints. Okay, so again, go to the top of the file. Don't bother editing anything below the dashed line. All you got to do is edit the restraints, right? So this is saying restrain in the X, restrain in the Y, restrain in the Z. If you wanted to change any of those or release any of those translational restraints, you would just type false instead of true. So we want the bottom of this thing to be pinned, right? So if I tab into edit mode, so hitting tab on the keyboard, you can see I was already in here previously playing around, and I've already got these nodes selected. So if I select those, and then I was to run that script with those nodes selected, that's what would generate the CSV file, right? So if I hit that and jump over to the desktop again, we can see we now have restraint data, which is the CSV file we need. If I now, let's say I wanted that one, and that, let me see. Let's say I wanted just that one to be fully pinned, right? Well, I just want to demonstrate how you'd get different kinds of restraints in the same model. So let's delete that off the desktop. Let's select that guy with those 3 set to true. Let's run that. Okay, that's fine. What you would then do is you would come over here and you would jump in and you would take that and drop it in here, copy and paste in. In fact, let's just do it, right? So let's just paste that in. Because we've edited the input data, it's got rid of all of our results for us. We'd have to run it. We've got to run it again. So you can see we now have one support here in the 3D view. Let's jump back over to our Blender model. Now let's say I just want these restrained in the vertical direction, right? That in Blender, the vertical direction is the Z direction, right? So I need to set the X to be false, and I need to set that to be false. That's the Y. And the Z, which in Blender is the vertical direction, is restrained, right? So now if I run that, boom, boom, let's, yeah, that's fine. Run that, jump back over here, not here, over to my desktop. Where am I? Here, jump in. We needed to close that guy out. We'll close that guy out as well. Let's open that again. Right, that was the restraints I just generated. Now you'll notice that there's a little quirk here, right? So in Blender, right, Blender is kind of peculiar in, well, I guess it's not peculiar in the sort of artistic 3D world, but Z is up in Blender, whereas in a lot of other applications, it's Y up, right? The Y axis is up. Now, you don't need to worry about that. You just obey Blender when you're in Blender and obey this coordinate system when you're over here. I've taken care of the translation between the two, just basically swapping the Y and Z coordinates in the back end in the code. You don't need to worry about that. But what it means is you'll notice that here that was false, false, true, but what got exported is false, true, false, because that's what we're going to bring over into our solver, right? So let's just take that, drop that in there, and you can see now our restraint model is different. We have just vertical restraint on these nodes and a full pin on that node, and in that case you run it again, generate a whole new set of results. Okay, we won't bother doing that just now. So that's how you deal with different types of restraint in the same model. You just do multiple exports and combine the data from each. The last thing we needed to do was to export some force data. I'm going to change them back to true in case I'm in here and I forget that I've done that. So I'll just leave them as true. So the next one is going to be the force data, right? So again, you just come in here, select the nodes that you wanted to have forces applied to. Here again, ignore, unless you want to dive into the code, ignore all this, you don't need it. All you need to do is edit these numbers here, right? What's the force applied in the X, in the Y, and then in the Z, right? So over here, it's going to be in Blender, that is, it's going to be a vertical force I want, right? So that's along the Z axis and it's negative. I want a downwards force. That means it's a negative number. So that's your negative 5,000, right? So 0, 0, negative 5,000. I'll run that. And because I ran it with these nodes selected, it will generate the CSV file over here, which is, you know, the relevant node numbers. And then the force here is that's going to be the X force. That would be, for us, that's the Y force, right? Notice that over in Blender it was 0, 0, minus 5,000, whereas when it got exported it was 0, minus 5,000. 0 again, because when we jump over here, Y is the vertical axis. I hope I'm not sort of flogging a dead horse here. You kind of get the point I'm trying to make. Right, so that's how you generate the data over in the Blender file. Now, that's all well and good. Let's just generate a model from scratch and bring that over, right? And so what I'm going to do is just delete that. So X delete, right? So that's what you're going to do when you download the template file. You're not going to want to reanalyze the structure that I've got sitting there, right? You got to delete it and put your own in, right? So let's just do a little bit of modeling on the fly here, right? So what do I want to do? I'm going to build model an inverted. Well, I guess whether it's inverted or not is kind of point of view. It's going to be a Toblerone truss, right? But one of the nice things about Blender is it's got fantastic modeling tools. I'm going to take that Toblerone truss and I'm going to curve it up, right? And you'll see how easy that is. It's a piece of cake. And then we'll generate data for that, bring it over and just run it through our solver. Right, so let's just get into this here then, right? So let me add in, and I'm not going to go through the steps of the modeling in major detail. It's only the same, probably half a dozen commands I'm using again and again and again. And so if you put some time into Blender, you'll pick this up really quick. So I'm going to generate a cone and I'm going to say I only want 3 vertices at the base of this thing. I'm going to tab into edit mode. Let me see, what do I want to do? I'm going to set that guy, delete him. I'm going to go into top down view. I'll hit S, Y, 0. I just want to flatten this thing out. Is that what I wanted to do? No, no, that's not quite what I wanted to do. So let's get rid of that and start that again. Let's add in was it a cone? I've built this thing once before, so I'm trying to remember what way I did it. Yeah, now I know what I want to do. I want to get rid of that guy. Delete that vertex and hit S, Y, 0. A to select everything, S, Y, 0 to flatten this thing out. Okay. What I'm going to do is rotate that about the X-axis, no, the Z-axis by 90 degrees. That's fine. I'm going to move it up by 1 meter, G, Z, 1. Let me turn on my screencast keys so you can actually see what I'm doing. So now I will select everything by hitting A, and I'm going to rotate. No, I'm going to rotate about the 3D cursor. Now I'm going to rotate by 30 degrees. Yeah, 30 degrees will do it. I'm going to put my 3D cursor up here now. Cursor to selected. Select everything. Shift D to duplicate it and rotate about the 3D cursor by a negative 60 degrees. I'm kind of building my little Toblerone here. And then I'm going to fill in a face or an edge and fill in an edge here. A to select everything. X, delete, only faces. Okay, so this is my basic Toblerone sort of shape here. So now what do I want to do? I want to generate many of these different things, right? So if I add a modifier, so let's go and add an array modifier. That'll do. So that's just going to generate lots of these. So I can move that up and generate plenty of them. So that is one Toblerone, one triangle pyramid thing is 2 meters across the base. So let's see, scale that by half. So if I go box select and shift S, cursor to selected, select everything and scale it by 0.5. Okay. And now, so let me see, that's going to make it easy for me to set the span of this thing. So I'm going to say I want 30 of them. Okay, that'll do. So there's 30 of my my little Toblerones here. So what I'll do next is I'll apply that modifier. And you got to apply it in object mode. Okay, that's good. Now, if I tab into edit mode, do I have duplicate vertices? I do, which just means I have multiple vertices at the same location. So if I A to select everything, right click and merge vertices by distance, you'll see that that got rid of 88 vertices. So now there is a single vertex occupying every point in space rather than multiple vertices over the same point. So now what I want to do is I want to generate a top boom arm that connects all of the apexes of these guys. So I'll just hit that guy and that guy, hit F to fill a face. I'm not going to do that for all the way along. Instead, I'm going to hit, let me see, P to separate by selection. That just creates a separate object. And now with this object selected, I'm going to apply a modifier to that guy, an array modifier. And how many did I say I had there? Was it 30? 30 will do, maybe one less, that's better. Okay, and let's apply that modifier. All right then, and let me see, I'm going to select that guy, Control J to make them all one object again, hit A to select everything in edit mode, right click and merge by distance. Did that get rid? Yeah, that got rid of 58 vertices. So now we have our Toblerone truss, right? We're nearly there. Now what I want to do is rotate this thing about the x-axis by 180 degrees because I just want to invert it. Let's go into side view mode. Let's see. That's going to currently be below the ground plane, and so I want to GZ move that up. We can just eyeball it for now, it doesn't really matter. So now I just want my out of plane bracing in this thing. So I'll tab into edit mode and I'll fill that guy, and basically this is just cross bracing for the transverse direction. So now I want to do the same trick to duplicate that all the way along, and so to do that I'm going to go into 2 to select that guy, P, separate by selection, and now I'm going to add an array modifier to that. Now that's what I want. Let's try, what was it, 29? No, not 29, probably half of that, which is it 15? Yeah, 15. Okay, so now I'm going to apply that modifier. That's fine. Select him, Control J, that joins them up. And now we have our basic Toblerone truss, right? So this is, we could bring that in and analyze that. That's no problem. But you could probably generate that data pretty easily, right? You could easily, it's doable. You could write up a little script, or maybe even at a stretch, you could pull something together in Excel that would generate all of the 3D coordinates of all these positions, you know, based on some parameters like spacing and height and what have you. And you could probably fairly easily write a script that defined all of these elements, which is just identifying the node numbers at each end of the element. But it's kind of tedious, right? And it would get much more tedious if you needed to do a structure like what I'm about to do. So let's imagine, let's go to side view here, right? So let's imagine what I want is this truss starts off at this level down here, but then it curves up in an S up here, right? So the way I'm going to do that is by using a tool called proportional editing in Blender, right? So I'm going to tab into edit mode. I'm going to hit O to turn it on, right? That's the button for it there, right? But shortcut key is O. And now watch what happens, right? If I come in and select, let me see, if I select these, oh, I should also remove duplicate vertices just before I forget, because you'll see there that I turn off proportional editing. I have multiple vertices occupying the same space. So if I hit A to select everything, right click, merge by distance, and that got rid of 45 duplicates. Now back to proportional editing, right? Into side view mode. Hit O to turn it on. And now hit GZ. Now let me see. S, cursor to selected. Yeah, right. So I want my fall off to be, Let's try smooth fall off. That just changes the shape of the fall off. You'll see what I mean. It's hard to explain. It's easier to show. GZ, and you can see what it does, right? That circle, which I can control the size of with my scroll wheel on my mouse button, that changes the influence, or the zone of influence for the command that I'm executing, which is to grab in the Z or vertical direction. So I can do things like, let's just say let's say I want a height difference of 1, 2, 3, 4, 5, 6, 7, 8. I don't know, something like that, maybe 8 meters. So I'll just hit 8, lock that in. And you can see I now have a nice, interesting structure that I can take over to my solver to solve. Now, to generate that data in anything other than a modeling tool, it doesn't have to be Blender, but you need a modeling tool, would be a real pain in the neck, right? It really would. But Blender makes this a piece of cake. And so, again, what I'm thinking of here is a lot of, student projects where you're asked to design a structure, come up with some interesting structure and design, and then do some structural analysis on it. It's kind of hard, to generate your structural models. You can use SketchUp. I see a lot of students using SketchUp, and that works, and works very well, in fact. But Blender is also a really good option. And now you have this tool, this solver tool, which integrates quite nicely with Blender. Right, so that's the structure. Now, one key thing you can't forget to do, and lots of people will forget to do this and contact me and ask me what's going wrong. It's because they've forgotten this part. Before you take anything out of Blender, before you export any data out of Blender, you've got to apply the transforms, right? What do I mean by that? If I go into N here and go to item, you'll see that, see these transforms, location, rotation, and scale. Well, scale is fine, that hasn't been changed, but you'll see there's a rotation of 180 applied here. What that means is, it's really hard to explain. What it means is, in a nutshell, model, and you bring it over to Blender, it won't appear like this, right? It will appear like this, but rotated by 180 degrees about the x-axis, so it'll appear upside down, so it won't reflect the rotation which I've applied. Anyway, the long and short of this is this, right? With your model selected, you want to go right. No, it's not that. It's Control A and apply all transforms. Now watch what happens to these numbers when I hit Control A and apply all transforms. They all go back to 0. Well, the scale and the rotation and the location go to 0, which I want, and the scale goes to 1, and it goes to 1 if it wasn't 1 previously. That's critical. The only way you should be exporting data out of Blender to use in anything I build, at least, is by having all your transforms applied, and that means having 0, 0, 0, 0, 0, 0, and 1, 1, 1. So in other words, if you bring a model from Blender into a solver and it doesn't look the way it looked in Blender, 99% chance you haven't applied your transforms. Okay, right, that's it. That's the model done. So let's just export it then. Right, so I'm going to jump over to my desktop first of all and get rid of these. I don't want those there. And let's just refresh that. We get a fresh page up. Okay, so we'll go to file number 1. And we can leave everything as it is and just export that. That's fine. Let's go to file number 2. Right, let's just imagine that this thing is tab into edit mode, select that guy and that guy, true, true, true. So that's going to be a pin and a pin. That's fine. And I want these two to be just restrained. I want them to be free in the X direction, right? So that means I want that to say false. And now I can run. I can't run it yet because if I run it now, it'll override what's there already. So let's just bring the data into our solver as we generate it. So let's take that and bring it over, drop it in there. That's fine. Let's take this, bring that over, drop it in there. And what was the other one? The other one was restraints. Let's take that, copy, and drop it in here. Okay, we can see our 2 pin restraints here. That's orthographic. Let's get rid of that. Orthographic, we don't want that. Let's turn off reset viewport on update, and the scale is a little bit on the big side. So let's just change that to be 0.2. Just to reduce it down a little bit. Okay, that's fine. Now let's generate those other supports. Which was these guys, so we can run our file again. It will override this file, but that's okay. Let's just close all these down while we're here. Jump back into Blender, run the file, jump over here, get that, and drop these in. Now notice the restraint models here will reflect the different kind of restraint. So notice it's not restrained in the X direction. And now we just got to apply some forces. So I'm just going to simulate hanging some weight from the bottom of this thing. So all the bottom nodes will be loaded. So to select all of those, I'm going to hit what is it, T to bring this guy up, change that to the lasso select, and then just click and drag, and then lasso select all of these bottom vertices. And let's just click that one as well. Okay, so with all these guys selected, let's just imagine, let me see, let's just imagine there's a negative, oh, I don't know, doesn't matter, negative 500 applied in the Z direction, and let's run that. Okay, that's fine. Let's come over here and then get this, drop that into here. All right, and let's, so the force is applied pretty much where we think it's going to be applied. We don't need to see those anymore. And at this point, we can go ahead and solve it. Let's take self-weight. Well, let's do it without self-weight first. Okay, so we've got some, let's look, green flags across the board, so that's good. And so now you can just basically go in and start having a look. So first thing to look at is probably the axial forces. So we can see our axial force distribution. Now you can see there's kind of it's kind of hard to see the color. That's just because the 3D element that represents the member at this scale, zoomed out this far, it's too small. And so to improve that, what you can do is you can increase the scale again, right? So you can see that beefs up the members, and it means it's a bigger member in the 3D viewport to add color to, and so the color appears proper. Okay, so like that's all we're really going to do. I'm not going to actually go in and start looking at the magnitudes of the forces and assessing whether or not they're okay. For that, you would scroll on down and look at your, where are we? Your stress utilization. So you can see at a max, our stress utilization is about 5%. So there's plenty of capacity left in this particular structure with these particular members and member properties. So it might be interesting to have a quick look at the deflection here. So we can just flick on the deflection, and we can see that at a scale of 1, the deflection is not a whole lot to see. So we could scale, manually or artificially, I should say, scale that up, and we can start seeing exaggerated deflected shape, which is obviously helpful because it gives us the qualitative deflected shape. If we want to see, obviously, the specific values of deflection, well, we could certainly scroll into any node of interest here, and in fact it might also be helpful to turn on wireframe mode. So let me see, I'm going to turn off my axial forces and turn on my wireframe, and we can see the deflection. Let's just scale it up. Let me see if I scale that up by, let's try 20. And now if I turn on my labels, we can see, we can see whatever deflection we're interested in. We're only kind of demonstrating here, so we're not really that interested to dig down into the quantitative values of deflection. Just scroll down to the deflection table. All right then, so let me just turn that off, and let me get rid of wireframe and zoom back out so we get a nice shot of our structure here. We never increased our window size. Let's do that there. Get a nice hero image of our shot of our structure here. So there you have it. That is, yeah, that'll do. There you have it. That is our 3D space frame truss solver. So, and of course, how you can use Blender with the solver to generate your structural models and to solve them. So as I said, it's really a learning tool, easy tool to use to generate the information for your 3D truss structures. And as I say, as I'm building this, or while I was building it, the people who I had in mind were those sort of first year, second year engineering students who are working on projects and need a quick, easy, free. You've access to most software as a student, so free isn't really that big of an issue for you, but a nice, quick and easy tool to use to generate some models of your structures. And of course you can generate some nice, I wouldn't say this is a rendering per se, which you could definitely take some screen grabs of this and generate some nice images of your structures. But I hope it's helpful. And as I say, if you're interested in how to actually write the code that actually does the structural analysis behind the scenes, head on over to, where are we? This course here, where I sort of walk through the Python code in detail, and you build your own version of your own Python code to do pretty much exactly what I'm doing here. All right, I'll leave it there for now.